Dipole-dipole forces. These are the result of interactions between two polar molecules. Hopefully, if you did not have me in General Chemistry 1, your professor in that class went over polar bonds and polar molecules. I'm not going to completely assume that you know how to do that here, but I'm going to go through this section fairly fast. So if you have not covered that, if you did not cover that in your Gen Chem 1 class, I would highly encourage you to go back to my videos from Gen Chem 1. They're on the same channel as this one, and find the videos that cover that. If I remember correctly, that was in Chapter 9. I think that was in the last chapter in Gen Chem 1. But it shouldn't be too hard to find. If it's not Chapter 9, then it's Chapter 8. Or sorry, not Chapter 9. Chapter 9 was gases. Sorry, I do them out of order. So it's either in Chapter 8 or Chapter 7. And I think I did those two chapters together, actually, in the lectures. So anyway, if you need to go back and review those, it's in Chapters 7 and 8, is where we go over polarity. And again, I think it's 8, but you can go back and check just to be sure. So when we're trying to determine if something can have dipole-dipole forces, the first thing we need to figure out is, does it have a dipole? Because if it does not have a dipole, then it is not capable of interacting with dipole-dipole forces. So to determine if our molecule has a dipole, we are going to use this handy-dandy flowchart. And this flowchart is essentially using a Lewis structure or a VSEPR structure, but the Lewis structures are easier to use, and so I just always use those. They use a Lewis structure to determine, and electronegativities as well, to determine if a molecule is polar. And if a molecule is polar, that by definition means that it has a dipole. So the questions that we ask ourselves here when we're trying to determine if a molecule is polar is, do we have any polar bonds? Because if we don't even have polar bonds in the first place, then we don't care to answer the rest of them. You must have polar bonds to have a polar molecule. And if we don't have polar bonds, then, well, easy enough, nonpolar. So it can't participate in dipole-dipole interactions. If we do have polar bonds, and just to remind you, a polar bond is any bond where two atoms are bonded together and the difference in their electronegativities is greater than 0.4. So if it's 0.4 and below, that is a non-polar bond, or what some people call a pure covalent bond. If the difference is 0.5 or greater, that would be polar. So the 0.4, 0.5, that's the cutoff. 0.4 and below, again, that's the difference between the two atoms. That would be nonpolar, so carbon, for example, is 2.5, hydrogen is 2.1. That is a difference of 0.4 between the two, and so that is a non-polar bond. Whereas carbon and oxygen is 3.5 actually, I think, if my memory serves. I believe oxygen is 3.5. I think oxygen is 3.5, nitrogen is 3. You can double check me on that. But either way, whether it's 3.5 or 3, the difference between these two is greater than 0.4, and so that would be a polar bond. So if we, once we know that we have polar bonds, we can go ahead and draw the Lewis structure, and then we are going to ask ourselves, does the central atom in this structure have any lone pairs? Because if it does, with very few exceptions, that is going to make the molecule polar. And we're going to ignore those exceptions for our purposes. They are there, they exist, and they're not super, super rare. Like, it's not that there's just one or two of them in existence. But compared to all the molecules where this is true, it's rare enough that we're just going to ignore them. If the central atom does not have any lone pairs on it, then we need to ask ourselves, are all the atoms bonded to the central atom identical? And if they are, then we have a non-polar molecule. So an example of this, and actually do we have some, no I don't, okay. So an example we did back in Gen Chem 1. It's a very famous example of this. Carbon, 2.5, chlorine is 3. Yeah, so oxygen is definitely 3.5. So chlorine is 3. That is a difference of 0.5, which is a polar bond. But because all of the chlorines have this exact same polar interaction with this carbon, they all are pulling on the electrons equally and in opposite directions, and so they just cancel each other out. And so you end up with a molecule that has polar bonds, but the molecule itself is nonpolar. If not everything attached to the central atom is the same, so if, for example, instead of having 4 chlorines, we had 3 chlorines and a hydrogen, now it's polar. Because no longer are you pulling on all the electrons equally. Some of them are getting canceled out, but not all of it. And so this ends up being a polar molecule. All right. So, just giving you an idea of the relative difference between dispersion and dipole-dipole in terms of their relative strength. Remember we said that boiling points can be used to guesstimate, for lack of a better term, the strength of intermolecular forces. So these two molecules have almost exactly the same mass. And they have very similar shapes as well, which is to say they're very simple. They're essentially just balls. And so the dispersion forces for these two are going to be almost identical because they have the same number of electrons practically. They have the same mass and essentially the same shape. But because formaldehyde has this polar bond, which gives it the capability of interacting with dipole-dipole forces, its boiling point is not -88 like ethane, which means that ethane boils at almost -90 degrees Celsius. Instead, its boiling point is -20. So about 70 degrees higher. You have to put significantly more energy into boiling formaldehyde than you do into boiling ethane. Now this is not to say that it's really difficult. Again, we're comparing the two things to each other. We're not saying, formaldehyde is difficult to boil. That's obviously not true. Like, it's very easy to boil. It would be difficult to keep it liquid, actually. But relative to the ethane, it boils very easily. So, if everything else is held relatively the same, if one thing has dipole-dipole interactions and the other one doesn't, the thing that has dipole-dipole interactions is going to be much more difficult to boil, much more difficult to melt, because there's a lot stronger interactions between the molecules holding them together. And so you can see that here as well, although this is slightly different because everything except for the propane here has dipole-dipole interactions. So the propane has no dipole-dipole, but then all the rest of these do. But notice that not all dipole-dipole interactions are made the same either. There are some dipole-dipole interactions that are stronger than others. And so they give you greater boiling points for those molecules here. Again, these are all relatively the same size, and actually almost exactly the same size in terms of what is present. And so it's not dispersion forces that are causing these boiling point changes. what's causing the change is the differences in the dipole moment, how strong the dipole-dipole interaction is. So up here at this end, where we have the strongest dipole moment, and again the dipole moment is just a measure of how strong the dipole is, the strongest dipole that we have on this page anyway has by far the highest boiling point of the 5 molecules here. So as we get stronger dipoles, the interaction becomes stronger as well. So dipole-dipole interactions are stronger than dispersion forces, but not every dipole-dipole interaction is the same. They're all a little bit different, at least. Alright, I think we have, so just one example here that I want to look at real quick. And then we will, and actually I probably should have had this one in the last video. Oh well. So this is actually about dispersion forces. So this question asks, order the following compounds of a group 14 element and hydrogen from lowest to highest boiling point. And it wants you to explain why you ordered them the way you did. So don't go and look these up. Actually think about, we have CH4, we have SiH4, germanium, H4, and tin. Tin hydride, I think is what that would be called. So, go ahead and pause the video, think about what we said about dispersion forces, and then order these with 1 being the lowest boiling point and 4 being the highest. So pause the video now and try to work that out. Alright, I hope you gave that a shot, and I also hope that you came up with the order 1, 2, 3, 4. If you look at the periodic table, the order that it's giving you here is just starting with carbon and then working your way down column 4A or 14, depending on which periodic table you're looking at. Carbon is the smallest, and then as you go down, you get to silicon, germanium, and tin. So the size of these molecules is increasing as we go from carbon to silicon to germanium to tin, getting larger molecules. And so because we're getting larger molecules, dispersion forces tell us that the rules for dispersion forces tell us that we should be getting larger dispersion forces as we go from the small molecule to the larger molecule. And so because we're getting larger dispersion forces, we would be getting higher boiling points as well. Alright, I think we'll call it there for this video. In the next video, oh yes, I remember why I put that here now actually. So the reason why I put this here and not earlier is because it leads in very well into this graph, which we're going to talk about in the next video. So I will see you there.